So the whole idea of potential energy, it's ultimately just the energy associated with position and some sort of force. So any given force that follows certain rules, basically that if you go in one direction, it's pushing back against you, and if you go in the other direction, it's, I guess ultimately it's just a force dependent on position. So where you are, or maybe how something is shaped, like how much a spring is compressed. The location or the length, the distance determines how much force there is. Any force like that, that follows certain rules like that, can be associated with the potential energy. And generally, if you got a force acting on an object, like for instance, let's say you are pushing on an object. And let's say you're pushing this against some force. Maybe there's some sort of resistance going on. Like maybe this is magnetic and it's being repelled by some other magnet over here. Or maybe you're pushing this against a spring. Maybe this is attached to a spring and you're trying to push on this object, but the spring is pushing back. So that means you're applying a force. But also the spring itself is pushing back. So you're applying a force to push this object, but the spring is pushing back against it. And if you want to make this object move, let's say we want this to move at constant speed, because if the speed is changing, what other type of energy is involved? Yeah, if the speed is changing, then kinetic energy is changing. If this object is moving at a constant speed, then it has kinetic energy, but its kinetic energy doesn't change, so we don't have to care about it. So let's assume that this is moving at a constant speed. Suppose this block is moving at a constant speed. If it's moving at a constant speed, what does that tell you about the force you're applying to it? Versus the force of the spring itself. What has to be true about those forces in order for the object to be not changing its speed? Greater than or equal to, let's check both of those. Let's say you're applying a force that is stronger than the force of the spring. That means the forces aren't balanced. So what's going to happen if the forces aren't balanced? If the spring is pushing to the left, but you're pushing harder to the right, what's going to happen to the object? It's not just going to move, because the force doesn't cause motion. An object can move without any forces at all. If you just got like a rock drifting through space, it's just going to keep drifting through space at the same speed forever with no forces acting on it at all. But if you got this rock drifting through space and you do apply a force to it, what's going to happen to it? Yeah, it's going to increase speed. Or if it's drifting this way and you apply a force in the opposite direction, it's going to slow down. It'll decrease its speed. A force doesn't cause motion. A force causes a change in motion. So if your applied force is stronger than the spring force, then the block is going to be getting faster and faster and faster, which means that it is not moving at a constant speed. If we want this to move at a constant speed, this applied force has to be exactly opposite to the spring force. Same strength, but opposite direction, so that the total force would be zero. If these forces cancel out, resulting in zero as the total force, then the object will move at constant speed. If one of them is stronger, like if the applied force is stronger, then the object is getting faster. If the spring force is stronger, then the object is getting slower. But the only way for the object to not be changing how fast it's moving is if the forces cancel out. So one way we can write that is that the applied force equals the opposite of the spring force. This is generally what has to be true. This is the condition that has to be met in order for the object to move at constant speed. The forces cancel out. In this case, that means the force you're applying has to be the exact opposite of the spring force or whatever other force you're acting against. For instance, if you're lifting an object, what force are you acting against? Yeah, you're acting against gravity. So as long as the object is not changing speed, whether you're lifting it at a constant speed or lowering it at a constant speed, or even just holding it still, the force you're applying to the object with your hands has to be the exact opposite of the force of gravity. So in general, if you want an object to be either at rest and continuing to be at rest, or moving and continuing to move at constant speed, the forces have to balance each other out. The force you're applying has to be the exact opposite of whatever natural force is already acting on the object. And that means if you want to calculate something about energy, what's the relationship between force and energy? How does force play into the idea of conservation of energy? Like if you're just pushing on an object and it's not moving, that doesn't really influence energy. But yeah, the idea of work. If you're pushing on an object as it moves some distance, you're doing work to it. So we can tie in the idea of force versus the idea of work. That work is force times distance. And let's say you're applying a force. You're doing work to the object by applying a force to it. So F would be force applied times the distance traveled. And work causes a change in what kind of energy here? If we're just moving this object at constant speed, what's the only kind of energy that would be changing? It can't be kinetic energy, right? Because if it's moving at constant speed, there's no change in kinetic energy. The kinetic energy just stays the same. So what type of energy are you changing? Yeah, that's going to be a potential energy. The work you're doing by applying this force to the moving object is a potential energy, a change in potential energy. So that means the change in potential energy of this object is the force you're applying times the distance traveled. But what do we know about the force you're applying if the speed is not changing? We can replace force applied with what else? The total force equals mass times acceleration. But that's ultimately why we know these are opposites. In general, the total, the sum of all the forces acting on the object equals mass times acceleration. But we know this object is not accelerating. We want the constant speed. So acceleration is going to be 0 because we're assuming constant speed. That's ultimately how we know these forces have to add up to 0, which means the applied force has to be the exact opposite of the spring force. And that's a substitution we can make. The fact that they have to add up to 0 so we get no acceleration means that the applied force must be the exact opposite of the spring force. So we can replace the applied force with negative force of the spring. So the change in potential energy should be negative force of the spring times delta x. And the negative here just represents direction. Negative in this context should be thought of as opposite direction. So the opposite of the force of the spring times the distance traveled. And delta x also has a positive or negative sign built in, depending on whether the object's moving to the left or right. One slight problem with this though, if you compress a spring, what happens to the force it's exerting on the block? Does that spring just keep exerting the same force forever? No, that's going to change, right? If you take a spring, yeah, you get an increase. If you compress the spring a little bit, you get a little bit of pushback. If you compress it more and more and more, it pushes back with a stronger and stronger force. So the force of the pushback, the force of the spring itself is going to change as you move. That means we can't write change in potential energy as just a single force times the distance, because that force is changing. So what we need to do instead is split this up into small pieces. If you look at this in terms of this distance traveled, like let's say it's going from X initial to, let's say you move it to here, X final. It's moving some distance delta X, but the force is changing. You start with very little force, then more force and more force and more force and more force. What we can do is split this interval up into a bunch of little pieces. We can take this little bit of distance times the force right now, plus this little bit of distance times the force right now, plus this little bit of distance times the force right now. We're taking force right now times a little bit of distance for each one of those tiny intervals and adding them up. And of course, we're going to get more accuracy the smaller the intervals are. Because if we look at just one big interval, we just get a very rough approximation. If we take two medium-sized intervals, it'll be a little more accurate. For smaller intervals, it'll be even more accurate. If we take like 100 tiny intervals, we get much more accurate. But what is this building up to? If you're approximating something by adding together lots of little bits of something, delta something, what does that turn into when you make this more and more accurate by making smaller and smaller intervals? Where have you seen this before in calculus? Yeah, this ultimately is an integral. Instead of writing this as a summation, we can write this as an integral. And then instead of calling this delta x, we can call this dx. That's really all this notation means. The integral sign, did they ever tell you what the integral sign actually means in calculus? What letter is this? Yeah, that's an S for summation. The integral sign literally just means a summation. Technically, it's the limit of the summation as you get more and more accurate. But this essentially means the summation of this thing times a tiny change in x. Dx means what happens to the change in x as you make the intervals smaller and smaller and smaller. So summation dx, or integral dx, just means the summation of all those tiny pieces, with the limit to getting smaller and smaller and smaller to make it more and more accurate. But this is generally how we can calculate any potential energy change. And technically, we should have from x initial to x final. In general, change in potential energy of any kind can always be written as integral of opposite of force. And that opposite is ultimately from the fact that the force you have to apply to make this happen is the opposite of the natural force, dx, from some initial location to some final location. So this is the definition of potential energy. Potential energy is defined based on integrating a force with respect to position, going back to the idea of work being force times distance. Any questions on that so far? So let's try using the idea of spring force to actually run this integral. The spring force, we've been talking a little bit about how the spring force changes depending on where you are. If you're at some equilibrium distance, which we usually call x equals 0, which you might consider to be the natural length or rest length of the spring. If you got a spring and it's neither compressed nor stretched, if it's just at its natural length, what force do you get? Like if I've just got a spring and I'm not pushing or pulling on it, how much force is the spring exerting? Yeah, none at all, zero force. If the spring's at its equilibrium distance, that means it's at its natural length. It's not exerting any force at all. In fact, that's really what equilibrium means. Equilibrium means a location where the force is zero. So equilibrium means there's no force. But let's say we have compressed the spring. Let's say we compress the spring to a shorter distance. And we would usually call that shorter distance a negative value for x. Because we've decreased the length of the spring. We've made the spring shorter. And left, right, up, down doesn't really matter here. Whichever direction the spring is oriented. If you compress the spring, we usually consider that the negative distance because you're making the spring shorter. If you stretch the spring, we would consider that the positive distance because you're making the spring longer. And in that case, if you've compressed the spring, do you get a force that's does the spring exert a force in the direction of further compression, or does the spring try to push back outwards? Yeah, the spring itself is going to push back outwards. And since that's in the direction trying to make the spring longer, we would consider that a positive force. So if the distance is if the compression is negative, if we get a negative amount of distance, then the force is positive. In other words, the spring force is pushing in the direction opposite to the displacement. Displace it in one direction, the spring pushes back in the other direction. It's trying to push back towards equilibrium. Or likewise, if you stretch the spring, if you stretch out the spring to make it longer, we increase the length, so we consider that a positive value for x. X is positive, greater than zero. But which direction is the force going to be? If you stretch out a spring, which direction is it pushing or pulling? Yeah, it's going to be pulling back towards equilibrium. And since that's pulling in a direction trying to make the spring shorter, we would consider that to be a negative force. So it looks like the force is going to be in a direction opposite to the displacement, which suggests we're going to need a negative sign in our formula. Also, let's say you compress the spring a little bit and you get a bit of force. If you compress the spring more, what would you expect to happen to the force? Like, let's say you compress the spring 1 centimeter and you feel how much force that is. Then you take the same spring and compress it 5 centimeters. What would you expect to happen to the force it's exerting? Yeah, the force is going to increase. And yeah, it will happen to be exactly 5 times as much. These end up being proportional. The force is proportional to the displacement. In the sense that if you take the displacement, if you displace it a certain amount, you get a certain amount of force. If you displace it, let's say 3 times as much, you get 3 times as much force. Which means that one of them can be written, as usual, as a constant times together. Force equals some constant times displacement. And that constant is usually called the spring constant, K. So K, the spring constant, essentially represents the stiffness or strength, sturdiness, I guess you might say, of the spring. A large K value means it takes a lot of force to compress it a little bit. So a very stiff spring. A small K value, close to 0, means it's very easy to compress the spring. So for instance, a slinky would have a very small value of K, close to 0. The big sturdy springs in car suspensions would have a much larger value of K because it's much more difficult to compress them. Also, since we need a negative x value to result in a positive force and a positive x value to result in a negative force, what else do we need in this equation to make that happen? How can we set things up so that F and X have opposite signs? What symbol could we put in the equation that would make that happen? Yeah, all we need is a negative sign. You could also accomplish this by treating K itself as a negative number. Then you wouldn't need the extra negative sign. But it's generally more conventional and easier to use if you treat K as a positive number and just have a negative sign separately in the equation. So this is generally the formula for the spring force. The amount of force a spring exerts is negative spring constant times X. Any questions on that so far? And this also means that it's very easy to determine the K value in a laboratory setting. In many cases, if you have a known spring, maybe you already know the K value, maybe it's labeled with the K value. But if you don't know the K value, you can measure force in a laboratory setting. If you've got a scale, you can measure the force. That's what a scale measures ultimately. So a scale can measure the force you're exerting, and a ruler can measure the distance it displaces it. So if you know both of those, you can just divide and find the K value in terms of newtons per meter. So that would be the units for K, newtons per meter. However, if we want to turn that into a potential energy, we can go back to this integral here. We're taking the integral of negative force with respect to position. So if we actually fill in this formula, force of the spring is negative Kx. If we rewrite force as negative Kx, but we also have this negative from the original definition of potential energy. These negatives cancel out, so we just get integral of Kx dx. And how would you integrate that, assuming K is a constant? What would be the integral of a constant times x dx? Yeah, the K is a constant, so we can pull that out, and x, when you integrate, becomes x to the 2 divided by 2. So Kx squared over 2. Or sometimes written as 1/2 Kx squared, or K over 2 x squared, all the same thing. But this is the typical formula for potential energy of a spring. 1/2 of the spring constant times the displacement squared. That's the amount of potential energy. Or since we usually care about the change, we could just fill in x initial and x final and subtract. So you fill in x final, you get 1/2 the spring constant times x final squared. Fill in x initial, 1/2 the spring constant times x initial squared. But what's the same in both of those terms? We've got 1/2 the spring constant times x final squared minus 1/2 the spring constant times x initial squared. They're different x values because we've got x final versus x initial. But yeah, it's the same spring constant because that's just a property of the spring. They both have K, and also they both have that divided by 2. So if K over 2 shows up in both terms, we can factor out K over 2 and get change in potential energy equals K over 2 times x final squared minus x initial squared. So that can be very useful as a formula for spring potential energy. 1/2 the spring constant times the difference in x squared. And so we would usually write that as 1/2 the spring constant times delta and then x squared in parentheses. The parentheses signifying that we're squaring both of the x values, initial and final, before we subtract. So the final x value squared minus the initial x value squared, and then multiply by K over 2, 1/2 the spring constant. So that's the formula for the change in spring potential energy. Any questions on that so far? So let's try a quick example here. If you have a spring that is, let's say, 2 meters long, and you want to compress it to, let's say, 0.5 meter long, that is 1/4 of its original length. And let's say we also know the spring constant. Let's say the spring constant is 30 newtons per meter. Given that information, if you want to compress this to 0.5 meter long, we can think of this in terms of conservation of energy. You're changing potential energy of the spring. And when you're compressing the spring, would you say you're increasing or decreasing the potential energy? Would you have to put energy into the system to make this happen, or take energy out of the system to make this happen? Yeah, you've got to put energy in. You're increasing the spring potential energy by compressing it. And one way to tell also is to look at the idea of the indicator. What's changing that we can measure that tells us that spring potential energy is what's involved here? What aspect of the spring is changing? Yeah, displacement. The x value, the distance, the length of the spring, position is changing. So we can use position, usually written as x, as the indicator here. However, the x value in this formula is being squared, which suggests that positive or negative doesn't really matter. Because if you square a positive, you get a positive. If you square a negative, you still get a positive. So the fact that the sign of the x value doesn't matter. In other words, it doesn't matter if you're compressing it or stretching it. Like for instance, compressing a spring 5 centimeters takes a certain amount of work. Taking the same spring and stretching it 5 centimeters requires the same amount of work. So to signify that we don't care about positive or negative sign, we usually write the x value in absolute value bars here. That is, the indicator is not x, the indicator is absolute value of x. And by compressing it, we are increasing the absolute value of x. And I think it's going to be easier to see why if we take a look at those initial and final values. What's the displacement at the very beginning before we compressed it? The length is 2 meters, but how much is it compressed? Yeah, it should be 0. We have not compressed it at all. It's at equilibrium. We define an equilibrium length to be 0 meters, in the sense that at equilibrium, we haven't stretched or compressed it at all. And x represents how much it has been compressed or stretched. Then at the end, how much have we compressed it? If we want the final length to be 0.5 meter, yeah, we compressed it 1.5 meters. So 1.5 meters. And technically, I think I would call that negative 1.5 meters, because by compressing it, we have shortened the length. So I would treat that as the negative direction. But ultimately, it doesn't matter because we're talking about absolute value. We're going to be squaring the x value in the end anyway, so it doesn't really matter whether it's positive or negative. So even though changing from 0 to negative 1.5 is technically a decrease in x, it's an increase in absolute value of x. Because absolute value of negative 1.5 is positive 1.5. And I think that's the only type of energy changing, so we can treat this as the whole system. Should we consider this to be an open system or a closed system? Closed system, we're not doing any work to it? Yeah, I think it should be open, because what are you doing to make this spring compress? Yeah, you're applying a force to do work to the object. You're applying work to the spring. So we should treat this as an open system with work entering the system, work done by your hands as you compress the spring. So this will be the complete energy interaction diagram. And we can turn that into an equation just by saying change in potential energy of the spring equals work. Formally, we could start with delta E total equals work plus heat, but potential energy of the spring is the only type of energy that's changing here. And there's no heat, there's just work. And then we can fill in the formula, same formula we got over here, 1/2 times the spring constant times delta x squared. Half the spring constant, which we know, times delta x squared in parentheses equals work. And in this case, I would not replace work with force times distance because the force is not constant. The idea that work is force times distance only applies if you're applying a constant amount of force. With a spring, you start by applying almost no force, and then you have to apply more and more force to get it to compress more. So work is not just force times distance. Technically, work is the integral of force dx. But let's just leave it as work for now. Figure out how much work you have to do to make this happen. We know the spring constant, 30 newtons per meter divided by 2. And delta x squared we can write as final x value squared minus initial x value squared. Final x value is -1.5. I think it's probably going to be easier to write that as an improper fraction, 3/2. So that's 3/2 meters squared. Technically -3/2, but the negative is going to drop out when we square it anyway. And then our initial x value was 0. So 0 meters squared. And then we can multiply that out, and that'll tell us how much work this takes. Half of 30 would be 15 newtons per meter. 3/2 squared would be 9/4 meters squared. And then we are also subtracting 0, so that doesn't change it. So we just have 15 times 9/4. So that'll be 15 times 9 is 135 fourths. And what would happen to the units of measurement here if we got newtons over meters times meters squared? Yeah, we get newtons times meters because one of the meters cancels out. And newtons times meters is the same thing as joules. So 135 over 4, which is what, 25 plus almost 9. So 33 and 3/4, I think. So that's how much work it would take to make this happen. To compress the spring to 1/2 meter long, in other words, to compress it by 1.5 meters of compression, is going to take 33 3/4 joules of work. Any questions on that so far? So there's the main idea of spring potential energy. As long as you've got an initial x value and a final x value, usually we use negative for compression and positive for stretching, but it ultimately doesn't matter whether it's positive or negative because we're going to be sparing it anyway. Then you can find the change in potential energy. In general, delta PE spring is going to be half the spring constant times the change in squared x value. Or if you don't care about delta, if you want to know how much spring potential energy is there right now, you can leave off the deltas and say spring potential energy is half the spring constant times x squared. So you can use that as a formula for spring potential energy. Any other questions on the spring potential energy? All right, then let's take a look at the gravitational potential energy as well. If you've got an object, let's say you just take an object and drop it. The force of gravity is going to be pulling it down. force of gravity. And how strong would you expect that force of gravity to be? Or what does the strength of the force of gravity depend on? Like if you've got several objects and gravity is pulling on all of them, what aspect of the object, yeah, the mass of the object is going to determine how strong the force of gravity is. So the force of gravity should be proportional to the mass. Like if you're lifting up an object, it's going to take a certain amount of difficulty, a certain amount of force to just to hold it in place. If the object is twice as massive, it's going to require twice as much force. So force of gravity should be proportional to mass, which means force of gravity equals mass times a constant. Anyone know what that constant happens to be? Or what it should be based on the idea that force equals mass times something? We often call it gravity, and yeah, 9.8, on Earth it's 9.8, but 9.8 what? What is that actually measuring? We often write it as m times g. Meters per second squared is what it needs to be. Yeah, because if you take a look at the units here, mass is measured in kilograms as usual. Force is measured in newtons. But newtons is actually kilograms times meters per second squared. So we need kilograms from mass, and we also need meters per second squared from g. So g is a quantity measured in meters per second squared, and that means it's an acceleration. So g here is actually the acceleration of gravity. Acceleration of gravity in the sense that if an object's in free fall, it's not falling at a constant speed, it's getting faster and faster and faster. G, the acceleration of gravity, describes how quickly the object is getting faster and faster if it's in free fall. And on Earth, the acceleration of gravity is about 9.8 meters per second squared. In the sense that if you've got a falling object and you measure its speed at a certain instant, and then measure its speed again 1 second later, the final speed will be 9.8 meters per second faster than the initial speed over the course of that 1 second. So this could also be read as 9.8 meters per second, the rate of change in speed. Also, since the force of gravity is pulling downwards, we usually write this as negative mg, if we care about direction, which we do here. So force of gravity is negative mg. M is the mass of the object. G is the acceleration of gravity, which on Earth is about 9.8 meters per second squared. We're often going to be rounding that off to 10 just to make the calculations easier. Though if you're going to be using a calculator for a problem anyway, you may as well use 9.8 to be more accurate, unless the problem specifically suggests to use 10. But for quick mental estimates, 10 is often close enough for a good general approximation. And G is going to be different if you're on a different planet. For instance, on the moon, it's only about 1/4 of that much. On Mars, it's, I think, about half of this much, maybe 1/3, something like that. So it depends on the planet you're on, both the mass of the planet and how big the planet is in terms of radius. It even varies slightly on Earth, depending on how close to the equator you are and how high elevation you are, how far from the planet's center. But on Earth, near sea level, it's about 9.8 meters per second squared. Any questions on that force of gravity so far? And one of the important things about that force is its constant, which is very different from the spring. With the spring, the more you compress or stretch the spring, the stronger the force gets. But with gravity, the force of gravity stays the same as you go up or down. If you go up a very long way, it does get weaker because you're getting further from the planet. But unless you're talking about really long distances, like space travel level of distances, this force does not change significantly. It depends only on the mass of the object. So that actually makes this integral much easier. We still want to integrate to find a change of potential energy. We still want to integrate negative force. In this case, the force is negative mg, so we're taking negative mg. And also, instead of calling it x, since we're talking about vertical motion, I'm going to call this y. So we're integrating negative mg with respect to y. from y initial, the initial height, to y final, the final height, if your object is changing its height. And notice that y does not show up in this formula for force at all. The force of gravity does not depend on height. You know, it's a constant that only depends on mass. The negatives cancel out, and we're really just integrating this constant mg with respect to y. And what's the integral of a constant with respect to y? Or to put it another way, we could pull out that constant, mg times integral dy. And what's integral dy? Yeah, it's just that constant times y. So mg times y. And again, going back to the original meaning of integral, this S stands for summation, dy means tiny piece of y. If we add together all the tiny pieces of y, we get y. So delta potential energy of gravity is going to be mg. And strictly speaking, since this is a definite integral, it's the final value minus the initial value. So just y final minus y initial. In other words, delta y. So we can use that as our formula for change in potential energy of gravity. Mass times gravity times change in height. Final height minus initial height. Or if you want the potential energy of gravity without the delta, that'll just be mgy. And this one's a little bit problematic because there isn't really an absolute 0 point for height. Y doesn't mean like some absolute height of like how far you are from the center of the earth. Y is going to be just measured from some convenient reference, maybe height above ground level, or height above sea level, or height above the tabletop, or something like that. So this is relative. You choose a coordinate system for Y. You choose a location and say, this location I'm going to call height 0 and measure everything above or below there. So the value you get for potential energy of gravity depends on your coordinate system, what location you're calling height 0. But the change in potential energy, it doesn't matter what coordinate system you're using. So just choose some location to call height 0, measure everything from there. The change is going to be some absolute amount, regardless of what coordinate system you're using. Any questions on that? So you've got formulas for change in spring potential energy, change in gravitational potential energy. We took a look at change in kinetic energy last time, 1/2 m times v squared, or delta v squared. So try applying those formulas to various examples, any practice problems you've got, and we can look at more examples next time. See you then.